I'm Marwa, I'm from Ford, and today I will be presenting our recent research effort at Ford in quantum computing. So before I start, I really like to acknowledge all the quantum computing team at Ford. So the work I'm presenting today, it's not individual, it's a teamwork, and they are all very smart people. So when we think about quantum computing, there are four fundamental approaches for quantum computing. We have at the bottom here the fault-tolerant quantum computer. Here is where we are expecting speed up. However, this hardware, as we know, is not exist today. Then we have the gate-based noisy intermediate scale quantum computing, and this is the noisy qubit. And here the main idea of this is that we want to reformulate the problem into a shallow circuit, execute the circuit, get the measurement before the noise hits you. In this here, the quantum advantage is still open questions. Whether there will be application in industry or no is also still unclear. Then we have the quantum-inspired computing. There is no really quantum here in terms of hardware, but it's mainly we are using or emulating quantum mechanic effect on classical computers. And it's going to be very useful for optimization and non-trivial optimization problems. Then we have the quantum annealing, and this is another type of quantum computer, but it's not a gate-based quantum computer. It's a type of quantum where you can physically start from a given initial Hamiltonian and slowly move this Hamiltonian to your the ground state of the problem Hamiltonian. And the concept that is used here is known as quantum adiabatic. So with this here, the second question is that, okay, then when we have this perfect quantum computer, what are the type of problems that we are going to be able to solve? So people in computer science classify the problem based on their complexity. And complexity of any algorithm, it's defined as how many operations it takes to solve a problem of increasing size. So, and we say that it's a problem, it's easy or no, or it is possible to solve it, and the algorithm is efficient if we are able to solve this problem in a polynomial time. So in classical computer, those problems that we can solve on a polynomial time are called P class. And then we have another class, it's called NP. Here we have a lot of important and interesting problem in industry. And simply in NP, it's a problem that if you know the solution, you can verify if it's correct or no. If you have a problem, and if I give you a solution, you can verify if this solution is correct or no in a polynomial time. But finding the solution is very hard. It can be exponential. Then we have the NP complete problems, and those are the hardest problems. And this is a typical examples we all know about is traveling salesman problem. Then we have the polynomial space. These are the type of the problem that needs a polynomial resources on classical computer, and it can be solved in exponential time or any time. We don't know, like it can be in polynomial, exponential, but it does require polynomial space. Then we have the exponential time. These are the problems, the hardest problem we have. So in quantum computers, the problems that we are going to be able to efficiently solve are called PQP. And this include all the P problems in classical, and in addition, small part of the NP problems. An example of this is the Schur algorithm that is going to be able to solve these factorization problems in a polynomial time. And we don't know any alternative classical algorithm that can solve the same problem in polynomial time in classical computer. But the rest of the problems that exist in NP problems and NP complete, as of today, there is no efficient algorithm is known to solve these problems. And we are not expecting maybe exponential. It may be some speed up, maybe some slight speed up compared to classical algorithm. But as of today, we don't know any efficient algorithm that can solve these other hard problems there. So based on that, at Ford, we are trying to identify those use cases that can take advantage of the quantum, and it might have a speed up compared to the classical algorithm. And our strategy here, so we are part of the research and advanced engineering team at Ford. We focus on what are in future, what are the near term, what are the far term in technology. And our research is divided into fundamental and development. The outcome of this research can be product focused or highly disruptive. So at the right bottom here, we have the highly development and product research. And that is mainly focused on near term, such as quantum inspired computing. And because this hardware is like you can have this today because it just requires classical computer, and this is available today. Then we have at the very top here, these are the very highly disruptive and fundamental research. And these are the problems that we want to try on quantum computer. And because this computer still not available today, still need to develop algorithms. So it's very fundamental and highly disruptive research. And this also gives us here with the development and fundamental research, we can really compare those methods that we cannot solve on classical, and we need really a real quantum devices for this. So based on that here, these are recent quantum computing research efforts at Ford. We have been focusing in two categories here, quantum inspired optimization. We have been testing use cases such as supply chain, traffic optimization, and recently at Ford, internally, we developed a method to solve permutation-based optimization problem, and we used it to solve the energy optimal routing. In addition to QIO, we are also investigating invariational quantum algorithms on NISQ devices, and here we are focusing have been testing so far two types of problem, optimization problem using QAOA, and we have been testing two use cases, binary paint shop problem for manufacturers and traffic flow optimization. Also use VQE for chemistry application such as battery, fuel cell, catalysis, and in my talk today, I will try to focus only on optimization. In Tuesday, I gave talk about battery materials, so I'm not going to be talking so much about this. So quantum-inspired optimization, it's simply the idea of this is when you have a non-trivial optimization problem, you have your landscape has many local minima, and you try to explore the entire landscape to find the global minima. If you try to do this classically, so the performance of the algorithm depends here on how quickly you can hop out on this local optima to explore the landscape and find the local minima, to find the global minima. So the time required to solve this problem depends on how like scale exponentially with the height of the barrier. So because you need to cross these barriers that exist, those optima. Quantum-inspired computing instead suggests an idea that uses the quantum mechanics, and instead of climbing this barrier, you tunnel through this barrier. And this can significantly speed up your calculations in your optimization problem to explore the landscape and find the global minima. And the method that used here is quantum Monte Carlo, and the advantage here is that you can implement this method today on devices we have, such as CPU, GPU, or even in custom devices such as FPGA. So recently at Ford, we have developed internally a method to solve a permutation-based optimization problem. To overcome the limitation and complexity exist in the traditional QIO method. So a typical example of the permutation-based optimization, it's a traveling salesman problem. When you have a route and you want to visit every point once, and you also want to find shortest path. The constraint in your problem here, you have the distance between 2 points. In the typical QIO method, what you have to do is that you convert this method into a binary matrix in a very given way. Then you create mini replica of this matrix, and you allow this replica to evolve. The way it evolves is that you simply make flip of this 1 to 0 or 0 to 1, and you validate this manipulation if it's valid or not based on some constraint. The implementation of this actually adds a lot of complexity, and also sometimes there are some problems that is not trivial to add this constraint in your problem, in your cost function. For example, like energy optimal routing that I will explain in the next slide. And What we did here, we reformulate this problem in a different way. So instead of starting from a binary matrix, we convert it into route vectors. And in this case here, you can see that there are two things can be noticed. First, you don't need to convert this problem into a binary. And second, in terms of memory, this is a huge saving. Going from a matrix to a vector, you really save memory. Then we create also a mini replica of this vector, and the way that this replica are manipulated, that in this case, you swap to adjacent point, and again, you have to, during this evolution, you validate if it's valid or no. And we have a patent is filed, and you can read more about the technical details of this work. So we have just the paper now available on arXiv. So we have used this problem we tested it on this energy optimal routing. And the energy optimal routing is simply you try to optimize your route based on the consumption of the energy. This is actually more complex than the traveling salesman problems, because optimizing based on the energy consumption, you are not just dependent on the distance between your point, but also dependent on the weight that between these 2 points. So to see this, so here on the right side here, I have to graph, go A, B, C, D. So you can see that there are 2 ways here. If you follow the path on the right, then you find that here, if you go AC first, you drop the heaviest weight. Then if you go from point B to D, now you have only 30 kilogram, although maybe the distance is the same, but now you have different weight. And this is, in this case, you consume 340 joule. And if you follow the other path here, now you drop first the lighter weight. And so if you go from point B to D, now you have a different weight. It's 8 kilogram, although the distance is the same. But now you consume more energy, 344. So trying to solve this problem using brute force method, it's a scale factorial, and this is even worse than exponential. So trying to solve this problem actually can help us to fuel really significantly the save, and so you can cost also the cost. And this is also good for the environment, so reducing the CO2 footprint. And in future, when we have all the electric vehicles become available also, we use them, then it's going to be, this is really important also because we need to manage the battery very well. So now here we start to see the performance of our method. So we compare here, so on the x-axis here, this is the number of points, and in the y on your route, and on the y-axis is the average of the number of the queries. Simply the number of time you call your cost function to calculate the energy. It's known that this is a really one of the most computationally cost here. And what we observe here is that with our tool, on average, this permutational QIO only explore 1.6% of the entire landscape, and it was able to find this global minima. So here we find that the global minima differ only from the exact method by almost 0.04%. So in exploring the only 1.6% of the entire landscape and find the global minima, this really significantly reduced the computational cost of this optimization problem. So now turn to the another second part, is that in addition to these QIO tools, we are also investigating in variational quantum algorithms to solve optimization problem as well as chemistry. So I will not talk here about what the variational quantum algorithm is. You all know that this is a hybrid algorithm that you try to solve the difficult part on the quantum devices using parameterized quantum circuit, and the parameter of this circuit is optimized on a classical optimizer. So we have been collaborating with the University of Melbourne in Australia with Professor Lloyd, and we have been using QAOA to investigate how can we use this tool for some optimization problems we have. One of these problems is a binary paint shop problem. So this is a problem in a manufacturer. So it's simply you want to, in this problem, you want to minimize the number of color swaps in a sequence of cars and under some constraint. And this is actually considered to be an NP-complete problem. So say, for example, we have bunches of cars. Some cars here, you have 5 cars of SUV, another 6 cars in sedan, and others are in trucks, and you want to have a different colors, and you want to paint those cars in a given way. And this is really it's a hard optimization problem. So solving it actually will help us to reduce the cost. So we have been testing 2 methods, recursive QAOA and QAOA, and we compare the results against some classical tools such as greedy algorithm as well as recursive greedy. And when we compare for this problem using the QAOA and recursive QAOA, and here we use pre-computed parameters using some techniques, we find that recursive QAOA reduce the number of C0 gates, so it helps us to significantly reduce circuit depths, which could be amenable for the near-term devices we have. And when we compare the results, we found that recursive QAOA give better solutions than QAOA. And comparing also this with the classical tools such as the greedy algorithm and recursive greedy, we find that recursive QAOA do better when we have 2+ numbers of cars. This form a kind of a basis for us to investigate more. I'm not claiming here any quantum advantage. That work has been done only in noiseless devices, and we don't know yet how noise might affect our results and how error mitigation scales these problems, how we scale this problem. We are not just interested in 12 cars or 14 cars. We need to see this for multi-cars. So this is still more work to be done. We are also investigating in chemistry for battery, and we have papers that's published, and it's available in arXiv. And so I'm not going to go here in details. In conclusion, what we observe is that quantum-inspired optimization can add a value today, and it might likely to outperform the quantum computing for this NISQ era. The reason for that is that for NISQ, we are limited with the number of qubits because of the noisy, so we need to use a short circuit. Now, the advantage of this against the classical, considering the scales we are trying to, we are operating at in industry, this is still unclear whether or not we will have a quantum advantage. But I think it's good to work on this area because we need to gain insights about quantum computing and develop the algorithms, understand what problems we really, it will take advantage of this quantum computing. As I said before, at the very beginning, we are expecting this quantum advantage when we have the fault tolerant. Here, for material science, there will be an exponential speed up, and that will help significantly for material discovery when we don't have experimental data available and we need to have some accurate tools to deal with. And then for optimization, we are only expecting to have a polynomial speed up. So far, it's only known to be quadratic using Grover algorithm, which is a search algorithm. It's not an optimization, but it can be used. And even though for it's quadratic, it is still good because considering, again, the scale we are operating at in industry. And with that, I thank you. Yeah, we are exploring possible use cases for quantum Monte Carlo for optimizations and trying to now explore what are the really use cases that will that can be which we can use quantum-inspired optimization such as quantum Monte Carlo to solve. So we just started on that.